Hello, so today we're beginning our discussions on derivatives by discussing what is a derivative and how it relates to what we call a tangent line problem, which is very common in our different AP Calc classes. So first off, the definition of the derivative. So the derivative function f of x is given by this. We have f with an apostrophe, so we call it like f prime of x, is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. As you remember from our section on limits, delta x is the change in x. So what this is saying is, as the change in x is getting closer and closer to 0, meaning there's virtually no change, it's very tiny, we want to see what happens to the function itself. And that's what's going to happen here. So today, and today only, we're going to discuss how to use the limit to evaluate how to find a derivative. It is a very slow and kind of annoying process. In general, we are going to do other methods, which we'll talk about in future videos. But for today, we will discuss how to use the limit process to evaluate how to find a derivative. Now, the nice thing about this stuff is the slope of the tangent line to a function can be found by finding the derivative of that function. So, in general, when we talk about functions, finding slopes of tangent lines, you need 2 points. But for the most part, if it's tangent to a function, you have the point it's tangent to, and that's it. So we can use these derivatives to write equations of tangent lines using the point it's tangent to and then finding the slope of the tangent line with the derivative. So that's what we're going to work with right here. So we want to find the slope of the tangent line to the graph of the function at the given point. So we find the slope first, then use the slope at the point to write the equation of the tangent line. So in order to do this, we need to find the value of the derivative. So we need to evaluate f of x and f of x plus delta x, which would be 3 minus 5 times x plus delta x. That'll work out to be 3 minus 5x minus 5 delta x. Again, the derivative is given by the limit as delta x approaches 0 of f of x plus delta x minus f of x all divided by delta x. So when we distribute the negative into that set of parentheses, we have the limits delta x approaches 0, 3 minus 5x minus 5 delta x minus 3 plus 5x all over delta x. And as we discussed last time when we saw this delta x in previous videos about about limits, everything that does not have delta x term is going to cancel out. Notice, positive 3, negative 3. Negative 5x, positive 5x. This leaves us with just simply negative 5 delta x over delta x, which they cancel, leaving just the answer is negative 5. So since the value of the limit of this particular function as delta x approaches 0 is negative 5, that is the slope of our tangent line, negative 5. Now that I have the slope, I plug the slope and the point into, you have 2 different options. If you remember from Algebra 1, you can plug into point-slope form or slope-intercept form and solve for b. It doesn't really matter. I'm going to plug into point-slope form. It's how I was taught. So y minus y1, so 8, equals m times x minus x1. So we have y minus 8 equals negative 5x minus 5. I add 8 to both sides, so y equals negative 5x plus 3. You'll notice the exact same equation as the function itself, which makes sense. Since the function is a linear line, the only way to be tangent to a linear line is if you are the exact same linear line. So for linear lines, it's a very trivial example. For more complex functions, though, it gets a little more interesting. Of course, for more complex functions, this f of x plus delta x part becomes very annoying, which is why, again, after this video, you'll never really want to ever do this process again. On the AP test, you don't want to waste this time. There's a much quicker way of finding that slope, that derivative, which we will talk about next time. So here's a little more of an interesting example. F of x equals x squared minus 9x. And again, I want to find the equation of the tangent line, so I need to find the slope of the tangent line, so I need to find the derivative at this particular point to negative 5. So I need to evaluate what f of x plus delta x is, which would be x plus delta x squared minus 9 times x plus delta x, Again, anywhere there's an x, I replace it with the expression x plus delta x. It's kind of like if you're finding f of 5, you'd plug in 5 everywhere there was an x. When I square that out, this becomes x squared plus 2x delta x plus delta x squared. Distribute the 9 and get negative 9x minus 9 delta x. So we're going to plug this into our limits. Our derivative is equal to the limits, as delta x approaches 0, of f of x plus delta x, so our x squared plus 2x delta x plus delta x squared minus 9x minus 9 delta x, and then minus the f of x, so x squared minus 9x, all over delta x. And again, if you notice, if we distribute the negative here, we have a negative x squared and a positive 9x. All the x squareds cancel. 9x's cancel, leaving just simply, limit as delta x approaches 0, of 2x delta x plus delta x squared minus 9 delta x. This has to happen every single time. After you work it out, all the non-delta x terms should cancel, leaving only the delta x terms left over. So I can cancel delta x in each one of these pieces, leaving just simply the limits as delta x approaches 0 of 2x plus delta x minus 9. Since delta x approaching 0, this goes away, leaving just 2x minus 9. That's the value of this derivative. Now, in order to find the slope, I have to plug in the x value into this function. So if I plug 2 into this function, we have 2 times 2 minus 9, which is 4 minus 9, which is also ironically a negative 5 slope. It happens to work out that way. So again, we have our slope of the tangent line. It's negative 5. I again plug into my point slope form. So y plus 5 equals negative 5 times x minus 2. Y plus 5 equals negative 5x plus 10. Subtract the 5 over, y equals negative 5x plus 5. That's the equation of our tangent line to the function at that particular point. Now again, you're going to see this kind of tangent line problem a lot on your different AP calculus tests. Maybe not necessarily a lot, but you will definitely see it at least once on every single test. The key is finding the derivative of the given function and evaluating that derivative at the given point. Once you have the point and the slope, you just plug into a simple point-slope form and get your equation of the line. However, you are not really going to want to ever do the x plus delta x part ever again. We will discuss how to deal with it next time, though. Very straightforward. So next time, again, we're going to talk about how to do derivatives much easier.